this is all the you guys see this one is this red dot, and that's why I'm recording this the screen capture on this class, and essentially from previous section I start with the number 10, which is nuclear chemistry, which one has the highest penetration power. That is a gamma particle. And then you can you balance this one? I think that you guys can try us for yourself. And the number 12 is fission, so you can balance it out with looking at xenon and strontium and looking at the periodic tables, and you can do that. Okay. So what I'm going to do today is I'm going to solve the 3 problems, and that will be my focus on today. Okay. So this problem says number 13. That's what I'm going to start. And the problem number 13 says it has a half-life of, okay, so I'm going to write T half-life is a 110 minute. Okay, so the time is there. And if the patient was given the initial dose of this milligram, and how long will take this fluorine 18 drops to 18 milligram? Okay, 83 milligram. So this is what you can find out here. Do you remember the half-life is a natural log 2 divided by k? So therefore, my k value is on half-life, which is a 110 minute, and ln2. Okay, so I can calculate those numbers, but I will just keep it as it is. This is what I did when I solved this problem by myself. And to make sure that you understand the time unit that you are seeing is the minute. Okay, so that's an information that is good for you to remember. And then you can choose any reaction, the first order reaction equation like this, minus kT. And here, what do they want is, they want how long will it take, right? How long will it take? And that means you need to find the time here. Okay, so that's the time that you need to find it. So, and then they give you this answer, the 83 is your time, 83 milligram. And your initial milligram is 248 milligram. So they cancel out. And then exponential to k is 110 ln2. My ln spelling is really kind of funny. So, okay, so ln2 times t. So once again you need to calculate based on this, right? So the way that you can solve this one is actually natural log 83 divided by 248 is minus ln2 110 times t, and this will be a number, right? And then this is all the numbers. And remember, this one itself is a negative, so your time is positive here. Okay. And if you plug it in, I plugged all the numbers, and then it tells me that's the one. This is a 174 minutes. Okay, this is a 174 minutes. One thing as a recap, I can tell you now here is, this is your original, and this is beyond what has half times, right? Half time, you're supposed to have a 1, 2, 4 milligram, right? 124 milligram, and this is even lower than that. So it should take longer than half-life, which is 110 minutes, right? And actually, so this by talking about this is out, and anything. And then actually you have to solve this equation, well, which is this is the same thing that, remember, I want to write in here, natural log a divided by a naught was minus kt, right? So that's the equation that you can use it right away. Either way, you'll get the answers like this. Okay, number 14 is a question about a little quite a difficult concept, that which nucleotide is most likely to undergo electron capture. Right? So if I put it this question in a different way, which nucleotide will be happy by acquiring an electron, right? They would like to capture the electron, means they have more, they have more proton that they need to, and this is something that is, where did I learn this, right? So let me show you, let me draw a diagram. This is a diagram that it was introduced as a value of, I think, the stability or something. And this is you show that there's a number of neutrons, and then this is a Z, which is this is something that is in your slide. This is a value, number of protons. And then this is a line that is N is same as Z, which is a number of proton is same as number of neutrons. So number of neutrons is same as number of protons. And most of the cases, that's a value of most those nuclei has this kind of tendency, which is up to, I think you'll start to remember, up to the 0 G to 20, you should have same N over Z is 1, and this section is like a 1.25 or something, and that's the one that has been discussed. Has anyone remember? Andrea, do you remember? Why did he talk? Do you remember this plot? If you guys can, anyway. And if guys can chat, yes, that will be good. Or putting any questions, I'll appreciate it, because it's like I'm talking to a wall, and then it's if the wall is talking to me, that would be better. Regular class, I can see you guys, your eyes and faces, and to see whether I'm doing good or not. I just have to continue. Okay. So in my, I think that I discussed this. So the thing is, the important one is, look at the other side. This is a one that actually, I want to put a unhappy face. This is unhappy. So what that means is, when your N value is smaller than Z, right? Well, if you want to call it N over Z is smaller than 1, your value is small. Okay, so it's a way that is an unhappy one. So this is a one that they try to avoid it. Okay, and if you look at now this going through the one by one, and if you look at the nitrogen, okay, the proton is 7, and the neutron is 7. I think that you are right on this the yellow line here. But if you look at the aluminum, so aluminum say 24, that means aluminum 24 make it, if I go to my aluminum is right there, that's the number 13, so that's a 13. So as far as a proton is concerned, that's a 13. Neutron is concerned, this is 11, right? So in this notation, N over Z for this aluminum is smaller than 1. And this is what I say, I'm not happy, okay? I want to go to this other side, not to be this side where I have a lot more proton than I needed. And how can I easily get rid of the proton? By combining them with an electron, you can turn that into protons, right? Turn the proton by capturing the electron, you can turn into a neutron. This is what I briefly discussed in the before. So if I write it this, the second case, aluminum, 1324. If they ever capture that electrons, what's going to happen is this will be 12 atomic number, and if I look at the periodic table, 12 means mg. Okay, so that's how I write. And then I will write the rest, which is 24. And then now look at this mg now. What is your n over z? Is 1, right? This is a very, very happy atoms, right? So this is good. This is an unhappy. By capturing the electron, you make things happy. So this is a 1 is going to happen. And so that's why this is going to be the answer. Okay, and you can continue to write it, look at it, but this is you can look at the slide, something looks like this, and then you see what you guys can find out. Okay, I will finish up the last question, and this is just involve a very careful calculation of the mass. So this one essentially starts from the fact that neutrons and protons do not have the same mass. So it is in the section called the mass effect and the binding energy, and that's what it says here. Okay, so this is a atomic mass unit, and F19, and then you're going to look at it. Okay, what's the atomic number of F? I don't want to remember, but I can look at the periodic table. So that's a number 9, right? So that's a number 9. And then you already said, okay, it has a proton of 9 proton, and number of neutron is 10 neutrons, and that's the isotope of the F19. And then and it says a proton has a mass of this AMU, and neutron has this mass of this AMU. And so that's what is now is before. You just have a collection of protons. So 9 protons, 10 neutrons. So just add it up. So that's what I mean by that. And what is now is an after is essentially F19. That's what I mean is this value itself, 18.99840,325. You need all these significant figures because it's very, very small changes in the numbers. So what I mean by add it up, just need to add it up. So this one is you have a 9. What is a proton, right? So proton has a mass of this 1.00. So 1.00, 7 to 8. 10 times neutron 1.008665. So having them add them together, that's a 19.15217. Okay, so if you have this essentially individual protons, okay, 1, 2, 3, 4. Okay, so and then if you have a different number individual neutrons, right, and then if you combine it into nuclei, there is a small change in the same number of protons, same number of neutrons, but there is a small numbers differences in AMU units. So what you need is this one needs to subtract it by 18.99840,325, and then you will see that 0.154 AMU. Okay, and then what is said in here is 1 AMU is equivalent to so many mega electron volt. So all you gotta do is just do using this one as your unit conversion. AMU 1 is same as a 931 mega electron volts. Okay, and then that can make you the AMU goes away, and you will get 143.2 mega electron volts. Okay, so that's the answer. Okay, so I solved these three problems, and then